Okay, I hope you had a nice coffee break with nice buns, and now we are ready to continue. And now we have another person historically from Uppsala. It's Alessandro, who will tell us something about integrated correlators and epsilon expansion, please.
Yeah, so thanks for the invitation. I'm very happy to be here and talk about some work, in principle, in collaboration with Joe, Anton, and Song Kao. But let me start, as every talk should start, with a question, which is why? Why should you care about this? But first, I think we should answer, why me? Why am I here talking about this line of research, and what is my relationship with Joe? So if you look at Joe's list of very long collaborators, and these are the ones who actually are going to speak today, and some have already spoken, my name is not there. So the question comes like, what am I doing here? Who am I? Why was I invited to this very nice day? Well, apparently Joe was my PhD advisor. So you say, this has to be true. When I first came to Uppsala, actually, it was winter, and I met Joe, and Joe looked at me and was like, who are you? And I was like, hi, I'm your new hire. That was our first interaction. And from then on, we tried to, did it move? Tried to attempt to work together. This has been part of my PhD. And Joe decided that the project that we should try and do was a bit outside of his knowledge. So you see, this is Joe's knowledge of physics, which is clearly broad and comprehensive. This was mine, which is stayed the same. And this is what he wanted us to do, which was here. So of course, this created a lot of required a lot of work and a lot of things, and we were very close to succeed. And then, unfortunately, nothing came out of it. But it taught us a very important lesson, which is never to forget what you have done during your PhD. But despite this, unsuccess, we actually had some success, but in something that is more related to experimental physics. And what do I mean by this? I mean some apparently studies of trajectories of tubers, which, as you can, unfortunately, the GIF doesn't work. But if you want, I can show it to you later. If whoever want to see this. And here is Joe showcasing his ability and how far away you can throw, and the good technique to do this. And here's me, who's like, yeah, good. I think I can do better. And no, I couldn't. But yeah, anyway, so this was our work together, and actually, it was based on some previous work by Joe and other people. And one of the reasons why, our summer parties became less fun, most probably. But anyway, that's tuber. It's a potato. It's a potato. Yeah, it's a potato. This is, Anyway, so despite all of these efforts of, actually, thanks to all of this, experimental efforts, I managed actually to graduate. And this is me and Joe, who is literally has not changed in the past 7 years. Is it correct? Or 6? I don't remember. No, 7, 6, 5, something like this. He has been the same. I have grown older and more tired, but yeah, he has stayed the same, always young. And this is us. I mean, this is me at the very fancy PhD defense, where actually I graduated with WAFA. So he was also receiving a PhD that day. And, this is something that not many people can tell. But yeah, so that said, so this is the end of my, my PhD. That's it. Mine and Joe's road bifurcated, and then I moved to my postdoc. And then at some point, I was missing Sweden so much that I said, no, I need to come back and finally try to do something with him. So then this is our second attempt of working together, which was, again, not very successful, but this time it's on me. Joe said, oh, we could try and do this thing, which, I know about. I was like, interesting. And I was like, let me think about it. And then nothing came out of it. But, one must not lose hope. So 2 years passed, we talked, and, we interacted. And, of course, Joe is a wonderful person to talk physics to. So this was very nice. And then, magically, at some point, we found something that actually was on, on the boundary, or if you want, in the intersection of Joe's knowledge and, what also I know. And I think this is what I will try and talk about today. So yeah, all of this to introduce the topic. And what is the topic? Well, the topic is a bit weird. This paper came out, and this paper introduced some nice ideas, said practically, let me try, I will explain why this could be useful. Let me try and compute, in dimensional regularization, two-point functions. So these are things that you may care about if you want to compute the spectrum, as Simon told us about. And he said, okay, let me try and compute a bunch of objects which are not so interesting, which are these protected operators. So by definition, protected operator should have, trivial two-point function, nothing too interesting about it. But I mean, let me try and see what happens. And apparently figured out that there were some properties that seems a bit weird. And by reading this paper and talking to Joe, I was like, oh, yeah, maybe we could, find some way of, proving or disproving whatever it's presented in this paper, and also hopefully learn something new with Anton and Sonkao as well. So what is this? Well, as I mentioned, so apparently this epsilon expansion. So if I compute a two-point function, I study all the Feynman diagrams, I do all this tedious computation. They seem to have some property which is called uniform transcendentality. I will explain what it is in the next slide. Just keep it in mind for now. And as I mentioned, these are not completely pointless. So at some point when you want to compute spinning three-point functions, you may need to normalize them. Actually, you should normalize them. And the normalization, since these things are divergent, it needs to be computed at high order in epsilon. So that's why Marco cared about these objects. And as I mentioned, this computation was done perturbatively up to 4 loops. This was what was available. Actually, 5 loops are available, but I think very difficult to implement. And all of this was done in momentum space. So what are we trying to compute is exactly this two-point function of 2, in this case, O2 operators. And the representation that I'm going to use is this one, where I have factored out some one loop result, and then I have a series of corrections, but higher order in lambda. Very well. So just to plug in some useful information, I'm going to use the bubble again in some point, and it's useful to know that, okay, you can compute the bubble with generic indices, and this is done by this ratio of gamma function. Just keep in mind that this is like a simple function, and all of this is it's only gammas. Very well, so you start looking at this perturbative result, and this is N1, and this N1 has this property of being uniform transcendental. What does it mean? It means that if I look at each order in epsilon, the sum of the indices of the zeta values actually are all equal. So in this case, I have zeta 3, zeta 4, and in this case, I have zeta 2, zeta 3, the sum of which is equal to zeta 5. And this continues to all order in epsilon. This is not something that you expect, especially because, I mean, this is known to happen in n equal 4, but I mean, it's a bit weird that this continues beyond when you expand in dimensional regularization, or at least it's not expected, and it's something a bit peculiar. And okay, actually this N1, which we're going to study as a simpler form, you can rewrite it as this two-point integral, okay, and as this form as a combination of this g function, which are the gamma function I was saying before. Okay, you might say, okay, fantastic, these are all simple zeta, so this is everything good, but if you look at the perturbative data and try to see what happens at higher order, so for the functions, for example, N3 and N2 at high enough epsilon order, you see that actually multi-zeta appears. So there is some non-triviality in this process, and there are some things which are actually not only generated by gamma functions. So there is some non-trivial functions in this. This is important to keep in mind, and it will be one of the interesting things that we can try and learn something new about. Okay, very well. So what was the whole point of Marco was actually to propose this conjecture. And what did the conjecture say? He said actually, if you look at the ratio between this two-point function and you normalize it by the by this bubble value, you see that at each order in the coupling, this is some simple prefactor, okay, which is some Pochhammer symbols and some factorials, and depends on a loop order, and it's determined only by odd zeta values. And okay, how did he found this? Well, he plugged in miraculously, I think, 4 orders of the expansion that he get, and then he figured out that okay, he could write this he could extract this formula. And for me, which I've spent most of my PhD hearing about localization, I was like, this looks a lot like a localization computation. And having Joe as a supervisor, I was like, who knows a lot about localization? Joe. And so the next step was actually to understand, how can we relate this to something that we can maybe compute through localization. And I remember that there is this nice paper about Joe, which is, I think, talked about, but should be talked about more, and where they actually were able to compute the partition function of supersymmetric theories with 8 and 16 supercharges in generic for spheres of generic dimension. This is work by Joe. There's also some work by Maxime and other people on this. And the idea is now to think if we can use this localization result on these spheres of the dimension to try and compute this two-point function. I will explain how. Let me just say, I guess localization is a pretty known concept, but let me try and introduce a bit what do I mean by it. I'm not the best person to do this, not an expert, but the idea is that you can add to your action something which is a Q a supersymmetric invariant object, and then you can add this. This will not change your partition function, and you can take the limit for t going to infinity, and then you can solve this path integral by doing a saddle point approximation. This will require you to compute some one-loop determinant. All of this is done in Joe's paper in detail, and then you can insert operator in the PPS locus on your manifold. In this case, the sphere is the north and the south pole. And once you do this, you have a system that order by order or non-perturbatively computes the partition function. I think in their paper they were looking at the free energy, and all of this can be done easily. So the thing is that what you at the end get out of this is some matrix model, and this matrix model is again some deformation of a Gaussian matrix model. So again, it can be integrated. There's no problem in studying it, and the bit which has all the interaction, if you want, or the thing that gives the epsilon corrections stays in this H function, which if I plug in d = 4 will go back to 1, and I will obtain the trivial result that tells me that okay, if you try and compute two-point function of n = 4, you should get something that doesn't depend on coupling. But if you try to go away from 4 minus 2 epsilon from 4, then you will get something which has some non-trivial function of d and lambda. We will have to ignore instantons for people who know a bit more about this, because they were not computed when they were studying this. It's a bit complicated to do them in d dimension, but okay, in principle, you have some under control this matrix model. Very well. Once we have this under control, how am I doing with time? Okay, very well. Okay, you're doing fine? Very good. Very well, I can drag it a bit more. Good. Very well. Too much. Very well, so the idea is then, okay, how do we compute this two-point function from localization? Well, there is some method that practically allows you to put down this insertion of your fields, and this is done by, okay, you need to take the logarithm of your partition function, and then you take two derivatives. Oh, there is a square here missing, and this will insert this O2 operator. So this you can do in general, and you can reconstruct something that looks a lot like what Marco was computing, which is the ratio of the two-point function computed in this way with the two-point function at 3 level, and this will have some epsilon expansion, and then we will have some. At each order in epsilon, we will have an expansion in the coupling. Okay, we can do this for O2 at whatever order in epsilon and lambda we want, and then we can start constructing our long table of results from localization. As you can see, actually, given the fact that we can also do this outside of the large N regime, but only in perturbation theory, because this will not be valid at strong coupling. And so we can start constructing all these different values, and then we can try and compare them with Marco has, and try to see if we can reason or find some way of proving his conjecture. And I think I need to wait. Okay, and we indeed can. So we can take the leading order in epsilon and try to put it in a nice form, and this is given into this way. And once again, it's very nice. So we only have odd zeta values as for him, and you have a lot of common factors that hints at that we're doing something right, but there is some extra factor, and this confuses us for a bit until we remembered that whatever you're doing in localization is actually computed in position space. Whatever Marco did was done in momentum space, and the two are actually related by a Fourier transform. So what you need to do is that you need to take the results of Marco, take a Fourier transform of them, and then if you do this, you can actually completely factor. This is exactly a factor that comes from a leading order in epsilon from this procedure. And then you can see that the two match exactly at leading order in epsilon. That's amazing. And actually, given that we have this form and also we have proven it, we can actually extend it and write it in a more useful way if one wants also to study the large lambda, the strong coupling expansion for this quantity. And this an important feature of this strong coupling expansion actually is that it contains some logarithm of the coupling, which is like a weird and peculiar feature, okay, of this result. And I want to stress again that, okay, this is computed from localization, and we have access to all order in perturbation theory. The other result was also done up to 4, and okay, it's very nice that the two match. And in principle, it is true that this works at leading order in epsilon. Very well, but then the question now comes is that what else can we do? And this is, of course, important because, okay, we proved this conjecture. It's very nice. We have under control all of this. But the thing is that, okay, can we do more? Can we extract more information? Well, the first thing we can do is that we can extend this to more general operators. So we can, for example, do this for higher charge operators. It follows a similar logic. You then need to do some more work at the level of localization. You need to define exactly how these are on the sphere and how they are on RD and how the two map works. But this has been already constructed, and so we have this under control. We're also able to match this with some results perturbative from Marco, and this for the few orders that we had, this seems to be the case that we match. Very well. So we can extend this conjecture to higher order in P. We can give you, if you want, the leading order in epsilon. But magically, at some point, while looking at our results, we notice something very peculiar, that if you take the formulation that I show here, and you take a derivative with respect to the coupling of this quantity, you end up on another result, which looks exactly like the 4-point integrated correlator that has been studied extensively in the literature. And this surprised us because it seems to say that, okay, you can deform you can break conformality. In here you add a mass. In here we're going away from 4 dimension. But it seems like at least a leading order, whatever you do, it seems to always get you something which is more or less related. And okay, you can have some diagrammatic understanding of why the two are related, because Tsongkao in one of his papers argued that, okay, once you compute in this integrated correlator, there is a measure missing here, but okay, let's argue that there is also a measure. What you can see is that you want to compute the period of this integral, and by doing so, you are practically computing exactly the 2-point integral that also Marco is computing. So the two are related trivially by practically, the two are related trivially in the sense that if I take this and I choose one of the parameterization for my external points on my correlator, and then I look at what I get the integrand that I'm left with is exactly the same integrand that I will get a leading order in epsilon for the what's it called, for the result in epsilon dimension. This is only valid at leading order in epsilon, because beyond this doesn't make any sense. So in some sort of sense, this is the truncation of this object. This one grows in epsilon, and so this is a map, only one order map. So this is a very interesting question, which is why does this happen? And we have not this under control, but it would be very interesting to understand what is the operator that you need to add to your action to actually obtain this, how you're deforming your action, what sort of operator you're adding to obtain this 2-point function. And okay, then the question, of course, that one would like to understand is, okay, can we push this to higher order in epsilon? And what I would like to tell you is yes. What I have to tell you is no, because this actually doesn't work beyond leading order in epsilon, which, okay, you could argue fair. You're not doing localization on sphere of integer dimension anymore. I don't think that whatever you're trying to do to map from SDE to RDE should work beyond leading order in epsilon. It's already very weird that it does. And actually, learning a bit from what happens for the 4-point correlator, we can argue that maybe what you need to do is that you need to shift the measure, and we could see, at least for the perturbative data that we have, that if one argues that the measure undoes the Fourier transform, we can match the epsilon square order by looking directly at Marco's perturbative result, which is very weird and very peculiar, but I mean, in some sort of sense would make sense. When you compute the 4-mass derivative correlator of this object, which should be related to the second order, if this relation is actually true, to the second order in epsilon derivative for this operator, you cannot use anymore the measure. You need to modify the measure and you integrate the correlator. And this could probably transform into a different choice of measure also for what we're trying to do. So it's also some epsilon dependent function that we need to plug in order to map these two. This is something that, yeah, we're still trying to figure out. So as I said, this was work in progress. And okay, very well. So what I've tried to convey today is that it's never too late to actually have a paper with your supervisor. Hopefully, that's we will see about this. And as I tried to mention, we proved some interesting conjecture regarding this expansion, epsilon expansion protected 2-point function, meaning the fact that are indeed uniform transcendental. The leading order in epsilon actually works as expected from a trivial interpolation from the perturbative data. Beyond this, we don't know how to say much. And as I mentioned, this was like we have some ideas on how to try and extend this, but it's difficult. You need to really understand how you're deforming your action. What is this? How does this epsilon deformation works? But surprisingly, this is one of the main points that I want to stress, is that there is this non-trivial relation that tells you that no matter how you do, no matter how you break this, no matter what you do, if you add a mass or if you deform in dimension, it seems like you end up always on the same sort of matrix model. And this is something which we were not expecting and is really surprising. So it would be very nice to understand this relation a bit better. And of course, there are still more things to figure out. As I mentioned, there is all of this higher order in epsilon, and also if there is maybe some relation between this epsilon and mass at the level of integral computation. If we can think of this as some more sort of mass regularization, well, this is some dim reg, and the two need to be related in some non-trivial way. This is probably also something that could relate these two correlator. Okay, with this I stop and I thank you. Well, I thank you, Joe, for all the time spent together and all our nice discussion about physics.
Well, so Alessandro, you talk too fast. You have 5 minutes.
Perfect. Okay. I can say more anecdotes if you want.
Do you have any anecdotes?
No, I don't have any. Enough embarrassment.
Okay. Any questions?
I have a very naive question. Yeah. A protected operator means that there are no corrections to the function. Is it because epsilon is non-zero that you have?
Yeah, exactly. Yeah, that's the only thing. So if you do epsilon 0, you get something which is completely protected. If you go away from, if you go into this epsilon expansion, this starts having correction which depends on lambda and on the coupling and epsilon, order by order.
I see.
Yeah. So if you look at the 2-point function, you have some function n, which is 1 plus epsilon correction. So when epsilon is 0, this is 1.
Could you start from, let's say you start from correlators that are protected in D equal 4. If you start from D equal 3 and you expand in epsilon, then you set epsilon to 1, what would you get?
That's a good question. We have not tried that, but I think that might not, I don't know if this has to, Well, if you don't get any poles, in principle, you should be able to analytically continue. The thing is that so you have a 2-point operator here, do this protecting and equal 3. Then you have an expansion in epsilon from localization, which doesn't converge to what you expect this to be. So it's a bit weird if you then put epsilon to 1 and then you manage somehow to arrive at something that actually makes sense in the equal 4. So it could be that maybe you're flowing to something else. It could be that, okay, maybe you're flowing to the correct thing only very close to these operators, and in the middle you need, as I said, to modify whatever the mapping from localization to flat space. I mean, we don't know how this would work, but this is one test that one can trivially do. Yeah.
Extrapolating the
yeah, sure. Yeah, no, that's indeed true. Yeah, but, yeah.
Okay, any other questions?
Hey, thank you. So you mentioned these multiple zeta values.
Mm-hmm.
Do you have any new insight in why they arise?
I mean, from the perturbative, they do, because you have some higher order hypergeometric function. They give you these multi-zeta values. From the matrix model computation, you cannot get them. This only gives you some ratio of, only gives you single zeta values. You cannot get anything more than that, because principle is just a one loop computation. So it's just gamma functions and nothing else. So the two seem to be incompatible. That's why the only reasonable thing you can think of is, okay, I modify how I map from the sphere to the flat space in a way which is, of course, not too trivial. So, or cancels the multi-zeta values in your flat space and then, okay, map only to things which are zeta values with one index, or has to do something which is integrating your results or doing some other weird things that allow you to construct actually multi-zeta values. Yeah, we don't know.
Okay, thanks.
Okay, any other questions? Okay, if not, let's thank Alessandro again.